Dear EANN conference attendees, my name is Pavel Gulyaev and I want you to present a report on my paper Detection of Shocking Images as a One-Class Classification using Convolutional and Siamese Neural Networks, written in collaboration with Andriy Filchenko. We both represent Laboratory of Machine Learning at ITMO University. The amount of information uploaded by users to social media instantly grows, and this information flow becomes more and more difficult to control in terms of preventing uploading of socially unacceptable content, which may be not safe for work or even not safe for life. Not safe for work content contains nudity, intense sexuality, profanity, violence, gore, or other disturbing subject matter, which usually are seen inappropriate if accessed in a public or formal environment, including a workplace or school. Not safe for life content is a subclass of not safe for work content that is horrifying, disgusting, offensive, or even mentally disturbing to the viewer. We decided not to embed too many images into the presentation. In this paper, we focus on detecting shocking images with convolutional neural networks. Several studies have already been conducted on this topic. Recognition of cruelty in images by Wang et al. Used bigger words approach on different image feature extraction algorithms and classify extracted features by SVM. This approach didn't consider the relationship on different parts of an image, which is critically important in cruelty recognition. CNNs are solving this problem. Zamgopoulos et al. Trained binary classification on semi-supervised data using pre-trained CNNs. Previously proposed work on this topic contained a number of problems which we aim to solve. These problems are as: first, lack of specific definition of shock content. Second, considering shocking content detection as a binary classification. Let us discuss these problems and their consequences in detail. The first problem encountered by developers of the shock image recognition system is the lack of specific definition of shock content. It is difficult to solve the classification problem when your domain is not specified. You cannot collect and label data properly in this case. For example, in one paper, shocking content was collected by sending relevant queries to the Google. As a result, the cruelty recognition classifier classified the images below as cruel. To overcome this drawback, we decided to narrow the concept of shock content to images of real cruelty over people, blood, mutilations, etc., and collect data more carefully. We did an additional data collection of border images. Border images consist of subclasses of images that misclassified by Zampoglow's model. Second problem is related to solving shocking content detection as a binary classification task trained on user reports. This approach has the following weaknesses. First, a model needs a many diverse non-shocking content and a large number of complaints to learn. Second, a model shows unpredictable behavior for objects that are different from those in the training sample. Third, the network quickly forgets or doesn't learn at all subclasses of shocking images such as, for instance, brain worms. Below are examples of incorrect binary classification illustrated in the short comments described. To overcome these limitations, we reduce the problem to the one-class classification task. In this task, shocking images are contrasted with all other existing images because it's impossible to correctly define the class of non-shocking images. This helps to eliminate the listed weaknesses of binary classification. First, there is no need for many non-shocking images. Second, a model learns only features of shocking content. If an image is dissimilar to any of the shocking images in the training sample, it's classified as non-shocking. Third, the amount of data for training is smaller, therefore the relative number of representatives of rare subclasses is larger, hence the model is easier to learn from them. We manually collected data in accordance with the information provided on the slide. Border shocking image class includes many subclasses. We considered 14. In the previous slide, you have already seen as an example of brainworms. Here you can see one of the most shocking non-shocking images, Lady Gaga in a mid-dress. The breakdown into the training, validation, and test sets was stratified. The image of each class and each boundary subclass was represented proportionally in 3 sets. For the validation set, 20% of all images were used. Thus, the ratio of classes was used 64%, 16%, and 20%. They compare the models with respect to their accuracy, precision, and recall in classifying shocking and non-shocking images. Additionally, we compare recall and precision measures for border shock and non-shock images separately. As a baseline solution, we used modern convolutional neural networks such as ImageNet-3, ResNet-50, and the implementation of ResNet-50 with fused layers, which means we extended last layer. They were trained in the binary classification setting. We used threshold movement to increase the recall of recognized and shock images and see how other metrics change. As a result, we can take ResNet-50 fused binary classification model as a baseline. First, we decided to use top layer of pre-trained CNN as features for one class SVM. We found out then learning these networks that replacement of a loss cross-entropy function to hinge loss function gives a significant increase in quality for OCSVM. This model is primitive enough and cannot handle with boundary images well enough. OCSVM trained on the features of ResNet-50 fused with hinge loss showed the best result. Another approach to solve one-class classification problem is using different type of autoencoders learned on images of the one class, shock content images, which would receive a smaller error for recovering images of this class in comparison with error of restoring any other random images submitted to the input. Setting the boundary of the recovery error will result in a classifier. We use 3 types of autoencoders: convolutional autoencoders to encode images, ordinary and sparse autoencoders to encode the values of the last layer of the pre-trained binary classification convolutional neural networks. When we detect shocking images with a one-class classification, we must take into account a large number of outliers due to a broad class definition. To solve this problem, it was proposed to use Siamese networks. Siamese network learns to determine how similar the pairs of outlier images are to each other and helps to consider the presence of very rare subclasses of images. During the exploitation of the system after the classification by the one-class classifier, an image is checked for similarity to a limited number of images poorly recognized by the network and the one-class classifier. If the image is similar to one representative of the rare subclasses, then the final answer is the class to which their subclass belongs. Otherwise, the prediction of the one-class classifier. When building Siamese networks, we choose the types of feature extraction, distance function, and matching classifier. Now consider the results of the building and training of models. Several convolutional autoencoders with different sizes and activation functions were built and trained, but all showed poor results. The best recovery error was shown by the 8-layer autoencoder, but the recovery threshold couldn't be found. Recovery errors for both classes are uniformly distributed across the sample. These are some factors that should be taken into consideration in the analysis of reasons for failure, including short network training time, convolutional autoencoder's decoder wasn't pre-trained, and too broad definition of class of shocking images for such a small sample. Sparse autoencoder can store a large amount of information in its internal representation and improve the basic solution with respect to all metrics. As it can be seen, sparse autoencoder using internal representation showed the best performance. As a result of all experiments, feed-forward neural network proved to be the best classifier for the Siamese network, so the table shows only the results of the work of the best models using other classifiers for the comparison. As it can be seen for the table, the Siamese network that has ResNet-50 fused as the feature extractor, the Euclidean distance, and feed-forward neural network as a classifier was the best. After finding the best Siamese network, we combined it with the best one-class classifier. Due to the class of shock image is containing a lot of very dissimilar subclasses, it was necessary to get the maximum amount of information about the data during the training, which was performed with the help of information stored in the internal representation of the sparse autoencoder. The best result is a model that uses a convolutional neural network ResNet50 fused as feature extractor for autoencoder and for Siamese network. Support vector machine trained on sparse autoencoder, internal representation and recovery representation as one class classifier, and Siamese network with the Euclidean distance between classified vector and feed-forward neural network as classifier. As it can be seen, the proposed solution significantly outperforms the baseline, and usage of Siamese networks helps to achieve the highest result. In this paper, we suggest a new method for shocking image detection. It includes using one-class classifiers for learning representation solely of shocking images and Siamese network for handling with the different and rare subclasses of shocking images. We use several methods of one-class classification, namely convolutional autoencoders, sparse autoencoders with pre-trained convolutional neural networks, and one-class support vector machines with pre-trained convolutional neural network. Due to the class of shock images containing a lot of very dissimilar subclasses, it was necessary to get the maximum amount of information about the data during the training, which was performed with the help of information stored in the internal representation of sparse autoencoder. As a result, sparse autoencoder recovery error combined with the vector of inner representation of images showed the best result. The achieved results are improved by using Siamese networks, which remember images representatives of especially rare subclasses. In the future, we are going to more intently consider the possibilities of using the Siamese network as an assistant to the main classifier. We plan to investigate whether the use of the Siamese network will reduce the number of errors of the classifier training in the process of operation, which means algorithm of online machine learning. Thank you for your attention.